All right, so let's talk about Lewis structures and shapes for compounds and molecules that have 5 and even 6 electron clouds. So please get out your shape sheet, and throughout this entire video, I would encourage you to pause the video and attempt these on your own as I work through the solutions. So our first example is going to be an AX subscript 5 example. So locate that on your shape sheet. And we're going to start with phosphorus pentafluoride. Now again, you're using all of those steps that we've discussed in the last couple videos for Lewis structures and determining overall shape. So as we move into this example here with 5 clouds, we will start with our basic skeletal structure here. So phosphorus, and this number will indicate the total number of valence electrons. Pentafluorine. So we're going to have a total of 5 coming off here. And for this particular structure, I'm going to indicate here the all the way around. So we should have fulfilling the octet rule, just like we practiced. And everybody here now should be happy. That's an electron there. Okay, so here's the overall structure. So when you use your shape sheet here, you can count the clouds. There's 5 clouds or electron groups. Remember 1, 2, 3, 4, 5. Don't forget that lone pairs on the central species also count as an electron cloud. Don't forget that double and triple bonds count as 1 electron cloud each. Okay, so we do not have any lone pairs, which means we are dealing with a trigonal bipyramidal structure. Now, the bond angles. Let's take a look at a PHET image here. And remember that this is a website. If you would like to open this in your browser while you're going through this video, I'd encourage that. Just Google PHET molecule shapes and it'll open the program that I showed you in the last video. Okay, so this gives you a really good idea. So we have what are called the axial bond angles and the equatorial bond angles. Now the axial bond angles are what are being shown in this image as 90 degrees. Okay, now if I take this molecule and I rotate it about its axis, and I'm going to rotate it from this point out toward the screen here, you'll see that the equatorial around the molecule has a bond angle of 120 degrees. Now, again, polarity and hybridization is a topic I'll cover in upcoming videos. Okay, so next example, sulfur tetrafluoride. So let's get started with that. And we have a total of 34 valence electrons. Again, hopefully you're pausing it and giving this one a shot, okay? When you work through the structure, you're going to end up with an expanded octet, and recall that elements in the 3rd period and beyond can take electrons and push them into the d orbitals, okay? So that can only occur in the 3rd and beyond. Sulfur is in the 3rd energy level, so it can have this expanded octet of 10. On your shape sheet here, we can go through, we have 5 clouds. Now remember, I'm not going to do this for everyone, but that lone pair on the central species is a cloud, cloud, cloud. So that's a total of 5 clouds or electron groups. We have 4 bonded atoms and 1 lone pair on the central species, gives us an AX4E structure. This is known as a trigonal planar bipyramidal seesaw. All right, and again, you can see its axial and equatorial angles are less than what we saw in the trigonal bipyramidal. That should make sense because that lone pair, which is able to move around a little bit more, is exerting some pressure. Or excuse me, not pressure, but electrostatic forces that are basically decreasing due to electron-electron repulsion. So let's look at what this molecule looks like here. You can see on the axial we have less than 90. This image is showing an 87.8. And for the equatorial, if we rotate this molecule, we have a 101.6, which is definitely less than 120. And remember, these are ideal bond angles shown on your shape sheet. In reality, we will see some small differences between these. Okay, so moving on to our next example here, we have a Chlorine Trifluoride. And you may be asking, wow, there's a lot of, why is fluorine and chlorine? What's going on here? Remember, those are the most electronegative species on the periodic table. So they have a very high probability. They are very good at attracting bonded electrons closer, okay, because they have this high electronegativity. All right, so chlorine trifluoride and 28 valence electrons. When you go through and do this, and I just realized on the last example I did not put all of these electrons around the ligand species. I apologize for that, but they should be there. That's on the last example. And for here, I'm going to end up with 2 lone pairs on the central species, and therefore 1, 2, 3, 4, 5 electron groups, or effective pairs, but I'm going to have only 3 bonded, whereas now I have 2 pairs that are lone. This is called a T-shaped, and we're going to see bond angles that are less than 90 all the way across. So again, this is a trigonal bipyramidal, but its molecular shape is called T-shaped. Ideal bond angles are less than 90 degrees for this particular molecule. And again, throughout, pause, do these on your own, go through all the motions, go through and calculate formal charges and those types of things to make sure that these are the best Lewis structures, which they are. If you're coming up with these on your own, I commend you. Xenon Difluoride. Okay, this is a pretty cool example. Xenon Difluoride. And at this point, you might be saying, xenon? Really? I thought it was a noble gas and it did not bond. At very high temperatures and under certain conditions, some of the noble gases lower in the group actually can be forced into forming bonds, and this is an example of that with our xenon difluoride. So you will end up here with a total of 3 lone pairs and 2 bonded pairs, which still gives you 5 electron groups, and it gives you a trigonal bipyramidal electron group shape, but a molecular shape of a linear 180. Check out this molecule here. Okay, so here you can see the 180 all the way across here with its 3 lone pairs. What's causing that? Electron-electron repulsion. Remember, those lone pairs are moving around the central atom a little bit more, whereas the bonded pairs are kind of locked in a little bit tighter. So the ones that move around are influencing the overall geometry and really chemical reactivity of the molecule. All right, moving on here. So this example, we're going to do sulfur hexafluoride, and it has 48 valence electrons. So sulfur, and that's 6. So little skeletal structure here. I hope the video is paused or you just unpaused it. So we have our 6 fluorines around the sulfur, and now I'm going to go through and satisfy the octet rule, and then I'll go through and make sure that formal charges make sense, which means they are minimized. If you get a formal charge of a +1 on one ligand species and the overall molecule is neutral, then hopefully you get a formal charge of -1 on another one, so those cancel out. Okay, so this is the structure. There are 6 electron groups. There are 0 lone pairs in this example. So this is an octahedral, bond angles of 90 degrees. Let's look at what this would look like all the way around this structure. You will see a 90-degree bond angles throughout. Okay, all right, so let's move on now to our next example, Bromine Pentafluoride. All right, 42 valence electrons and 5 ligand fluorines. Okay, moving through. All right, okay, you're gonna end up with an extra 2 there for the bromine. And moving along. Okay. All right, so if you look, you'll see that this structure would be acceptable. Bromine can have an expanded octet, and indeed it does with 2, 4, 6, 8, 10, 12. Where did those additional 4 electrons go? They were pushed into the d subshell. Okay, so they are in a d orbital. All right, so if you go through and count, you'll see you have 6 electron clouds, but you have 1 lone pair in this instance, which means we have a molecular shape known as a square pyramidal. It looks like this, and you can see the lone pair up here, which is going to influence the overall geometry and the bond angles. Because they are able to move around, they're going to decrease what would be ideal from 90 to less than 90. In this case, it's showing 84.8 degrees. All right, chlorine tetrafluoride anion. So this one is an example of a square planar, and I'm just gonna do it like this for the sake of time, and I want you to give this a shot on your own, and we'll talk about it in class. But the key to this one is it's an anion, so don't forget, it's not, 7 times 5 is 35 plus 1 electron. Remember, this group has taken 1 additional electron, so you need 36 valence electrons, which will give you 90-degree angles again. But because now you're going to end up with 2 lone pairs on that central atom, you're going to end up with a new molecular shape called a square planar. All right, so now I want you to go back through the problem set and work through any 5 and 6 cloud examples that I have as we continue to explore our Georgia Standards of Excellence and bonding. I'll see you guys in class.